We're running ezCon on one data file. We think this is a longer data file and will educate us more. What was the last one? 3 minutes, I guess?
3 minutes and 3.1
So it's
minutes.
going to be 6 minutes or so, at least, to grind all this out. This is also using the fast math. Halfway up the screen, I can see ezAstro math equals 1. Do you see that on the left?
Uh,
ezCon Astro Math. Up above that. Keep going. Another paragraph. There we are. The value for one of the parameters, ezCon Astro Math, is 1. That turns out to be the fast math. I have found some math errors in that. I'm going to try to fix that bug. And so we found better to use the slow one, which is value number 2. Currently on the web, the default is to use ezCon Astro Math with a value of 2, unless you try to change it.
is that something that I can change myself, or is that part of the
Yes,
program?
you can. We're going to learn together how what's going on here. Somehow the ezCon Astro Math works fine with the data that I collect. Is that because I'm in the right place on the Earth? I don't know.
What is that astromath? What does it do?
There are different libraries to do the math.
I see.
The number 2 is the official, but I was thinking that I found a faster way to do it by porting some code out of another program. And
Is
I
that,
thought it was working fine, but now I find it isn't. So
is
I
that a
got to,
program that you coded because it starts with ezCon, or is that something that it's out there for uh,
um,
Linux?
one of the things we did to install this program was get a requirement called AstroPy. It was a library that
Okay.
we called in. And the value of 2 on that parameter would use AstroPy for a library. This is explained in that help screen we talked about, like so many things. It's got a lot of knobs, and so I'm pleased to help walk through getting all this going. Well, that was actually pretty quick. I didn't see even how many samples there were, so that's fine.
Like 8,000 samples or something like that.
Well, that's about double the 4,000 we saw before. That's good. The plots will take a little bit longer because they've got twice as many data points to work on. That's fine. And it's counting down. We're at 68. We're trying to count down to 1 because at this point we've chosen every graph to be plotted.
Now, as this is being plotted right now, if we go to the other folder, you can see the new.
Yeah, in fact, yeah. So we've kind of climbed up to about 17 in the counting. So we could certainly look at the first one. Let's go over to the file manager as this thing's going. We will find the fail. Let's leave this. Yeah, don't kill it.
No,
It
no, I'm not
saves,
going to kill
it
it.
saves us some typing. Let's go up on directory where the demo is. That's where we started this command prompt. Um, and let's click on the first purple one. Yeah, that guy. Okay. I see a lot of purple in the middle, and I see kind of a faint something going on in there.
Right, I see it.
Software will try to pull that faint something out above the other noise. But this is the raw samples um, showing all the sample spectrum information uh, by sample number. Each spectrum that you were familiar with is a vertical line um, on this graph. This is representing things by color, and so it's called a heat map. Heat map. And you can see the value of those points on the graph by their color, explained on the right with a value. Oh, I think I know what's
I
going on
see
here.
a very faint
Yeah.
signal right here, and this is interference, I'm sure.
Correct. And I'm going to start showing you some of that as we go. Let's click on the right keyboard arrow and look at the next graph. In fact, let's maximize this thing too. That's another way, just so it records bigger. Uh, right arrow on the keyboard or clicking right there. We've moved to the next graph. It looks much like what we saw before. It has a different title on the left-hand side. And if you move way up into the black, way off to the left, keep going to the left, even more left, off the page, you can see the file name. We're up to ezCon 002. All the plots begin with ezCon. They are followed by 3 digits. We're up to 2. And then it tries to provide a description after that, and then .png, the type of graphics file that gets recorded.
So this would be the antenna raw signal without being processed.
Yes, it doesn't have to do with reference signals. We'll get to that stuff later. These are antenna signals. This is what came in from above into your antenna. Let's go to the right again somehow. This is the next graph, and this is now after any filtering of the previous data, and we didn't do any. And so that's why all these 3 graphs look the same. These are all ant samples, antenna samples, and we haven't done any filtering. Let's go to the right. For each vertical line, which is a sample, which is the maximum value? So for every vertical line, there's a green dot. It doesn't make much sense now, but we're going to understand this better as we go along. And then, which is the most powerful, highest value of all the green dots? And I put a yellow dot on it. And what I think we're seeing here is there's a bunch of RFI right at that yellow dot, kind of a spike, as if there was lightning or something like that, or a neighbor. And this is helpful just to kind of understand what's going on. The software will try to walk past that and filter that out. Let's keep going to the right. This is references. I said we really didn't have any. So it used the very first sample and copied it as if it was every other reference sample. That's why they're all horizontal lines. Whatever was on the very first 00 sample got copied as if it as a reference for all the other numbers. This number has to be equal to the same number of ant samples. Let's go to the right. We'll use this in more advanced ways later. This is the maximum. Those are little green dots all along there. That's very dull. Go to the right. All right, we've tried to process it a little bit. It looks kind of like what it was before. If we go to the right, we might see a little bit more. Here's the maxes. Everything looks the same so far, although something's trying to happen in the middle that we see in all these plots so far. Let's go to the right. And go to the right again. Yep. All right, to the right again. I'm doing the best to calculate it out, and I'm having trouble. I think we'll see why later on. Um, so far, it's hard to pull out any signal here at all. Let's go to the right.
It may be that the hydrogen gas was not there when these samples were taken, but
We're going to find out. They may be overloaded by another strong signal, which confuses everything. I see a blur in there, so there is some hope.
right here, yeah.
Well, right there in the middle, there's kind of a splotch, but we need to do much better than that. We need to get rid of some of this RFI. Let's go to the right. Yeah, okay. And so it's trying to do things that we can hardly see, but it all makes sense, but it's just so faint. To the right, we want to see some others. Oh, well, that's getting good. All
Oh,
right. What I did here was some math, and we can do it more precisely. Remember how the yellow dot was up on the left-hand side?
Right.
I trimmed it off. I made it go away. I ignored it,
Oh,
or at least the program did. And since I programmed it, that's what I'm saying. Um, Suddenly, other things show up. Now, let's use this and try to understand what's going on later on. But we see some kind of curvy thing that's brighter color than others. The
yeah.
yellow is a big number. It kind of goes along right around the zero frequency shown on the left y-axis,
Yeah.
and it seems to get brighter twice a day. That's all very encouraging.
No,
This is
yeah.
that very faint signal I could see in the purple of the previous plots. This was my hope that it was being this signal was being overwhelmed by a kind of a stroke of lightning that was a big number that overexposed our eyes. We couldn't see this data. The software finally trimmed off that bad news, and now we can see this faint signal down below. Hooray, analysis. If you held an antenna up about 45 degrees or so, and what was this elevation? Do you recall?
Yeah, zenith.
Oh, okay, up at 90 degrees. Well, that's fine. 45 might even be stronger, at least for us here in the northern hemisphere. But 90 would be just fine. Uh,
But what I'm going to do is I'm going to lock the azimuth because it's kind of free floating, and if there's wind, it weather vanes. So I'm going to go ahead and mechanically lock it in the azimuth portion, so I'll be able to start going down every 10 degrees, 40 or
that's the right way to do it. Drift scans work just fine for this. That's what the program was intended for.
okay.
Um, if you point it straight up over near Los Angeles, where you are, the Milky Way galaxy will be directly overhead. It turns out about twice a day. And those are the two bright spots we see, kind of in the middle and over on the right side. In fact, it kind of overlaps from the previous day way over on the left. And so two large bright spots, one of them near the right edge. Great. Okay, let's go to the right and take a look at a different way to see this. That's where all the maximum values are. That's looking pretty good. It's all around zero after we've done some math on it. So far, my math is working out okay. Let's continue on with this thing then. Yeah, all right. So for every sample, there is a bunch of data. And so now we start walking through all that stuff. First off, there's time. Along the bottom is the sample number and the time in UTC when it occurred. It's kind of a strange plot, but for each one of those sample numbers, what is the time? And that's written on the y-axis. It starts at 0. That's because UTC 0 is when the file began. And it writes all the way up to a value of 1 in the top right-hand corner, because that's when this file ended and a new file began at midnight UTC. All right, so the values go from 0 to 1. This is a relative time counted in fractional days. Good. Next. During that time period, with the math grinding away, it knows where it's pointing at the sky. It knows where you are, where the observatory is, and it knows what the time is in somehow eventually in UTC. And therefore, directly above would be a point on the star sky. What is the right ascension for that point? Turns out it started up about 22 or so, when it climbed all the way up to 24. And then suddenly the next sample was down at the bottom at 0 because it wraps around. After 24 on the right ascension, it becomes 0 right next to it. And then it climbs very linearly all the way up, sample by sample, up to the point, same value where it began. And it begins the next day, 24 hours later. That all makes sense.
Yeah.
Let's go to the right. That was right ascension. Declination has to do with elevation and where you are on the earth. And so it did some math and it said you were looking at a declination on the star sky of about what, 37 or so, something like that.
Yeah.
And you never changed it. And that makes sense. Now, so where are you on the earth?
Uh,
You're at
actually,
latitude what?
34.80,
Okay. And so it turns out
34.12,
if you looked straight up, you would be looking at the stars at that number declination.
which
If
is
you were on the equator at 0 latitude on Earth, the stars above you would be at declination 0. And if you were up at the North Pole looking straight up, you'd see the North Star directly above you 24 hours a day at 90 degrees declination. This all makes sense.
absolutely.
And so that's true for every sample. It's a very dull plot. It can get more complex. Let's go to the right. All right. Well, if you convert that right ascension and declination into galactic latitude and longitude, you get weird graphs. But hooray for computer math. Yeah, they wobble around. They may go up to 90 and then suddenly down to a lower number or something, or I guess higher. Um, I trust the math. We'll test it with plots later on. This is latitude, how high it is above and below the galactic plane, which would be at 0. The next one is longitude. Galactic longitude is when you look directly from the Earth, of course, as you look at the center of the galaxy and have the plane to the left and the right of you. To the left is called positive galactic longitude. So it's above the 0 there in this plot on the y-axis. And it climbs up as the day progresses. In this case, it got all the way up to 180 positive, and then suddenly it snapped down to the bottom to minus 180, climbed up a little bit, made a little bump, and then did the reverse. It went down below minus 180, which means it's plus 180, and did another weird curve. But these are very creative curves. They have multiple trigonomic functions to define them. Let's go to the right. Hooray for computers. As you look out at the sky, uh, things are moving towards you and away from you in a complex way. Some of that is reflected on this graph. If we look out on the Earth, and as the Earth goes around the sun, it will look like as if the galaxy gas is coming at us because we're actually moving towards it. And then 12 hours later, we'll be on the backside of the Earth, moving away from some galactic gas out there directly above us or out in front of the antenna. Um, and it will look like it's moving away from us.
Mm.
Well, to do all this math, if we're studying the galaxy, we want to remove all this Earth motion stuff. And so that's what this graph is doing. It'll be a wavy line normally, um, and it's measured in kilometers per second. So this is a correction factor we need to use to remove the Earth's motion from our study of the galaxy. It's interesting that it's not centered on 0. It has a whole bunch of more negative motion, negative numbers on this graph than positive numbers. Okay, interesting.
So it's like a calibrating, it's like a flat uh, image for visual. It calibrates out all the Earth motion, the errors that it's a calibrating.
Well, I understand what you're trying to say, that there's a correction going on here. But having to do with imagery and flat and whites, we'll see later on. Um, and it doesn't apply so neatly to this.
Okay.
method. But this is a correction that is calculated by the math, knowing where you are on the Earth, what you're pointing at, and what time it is, um, that we use as a correction value to improve our data.
Wow.
Go to the right. Um, we had that plot before, the heat map, and that was mostly purple. And for every vertical line, I say that was a spectrum of a sample, one sample. What is the average value for all the numbers along that sample? And I come up with one number for every sample, and that's what this plot is. You can see it jumps around a bit. Uh, Generally, it's about like 5.72 or something. It's not jumping around that much. Um, but there are a bunch of spikes, and so something's going on with our data. We've collected some other weird stuff. There are ways we can make that go away. We might just pick another day that doesn't have that. We might get lucky. Otherwise, we have to process this some more. ezCon knows how to do all this stuff. We just have to tell it what to do. Let's go to the right. That was the antenna average. This is the antenna maximum. Sure enough, in the top left of that purple graph we saw in the beginning,
Yeah.
uh, it had some dots way up on the upper left-hand corner. And now we see their values. For every sample, what is the value of the maximum number of that sample? And so we saw some interference. This is what made the graph all purple. Um, what we may do is run it again starting at about sample 2000 and ignore everything in the beginning of it. It's kind of interesting that we see two bumps at about sample 4000 in the middle, and on the right hand side we see a little bump. So that was the bright yellow things we saw later on after ezCon processed it a little bit. Interesting. So we saw the average value for each spectrum on the previous plot, and this is the maximum value for each sample spectrum. Next. We do the same thing for reference. I told you reference was simply a copy of the first sample, so this is really dull. It's the same average all the way across. Next. And in the same way, this is the maximum value for the same value all the way across. We can use this more complicated ways. Uh, it'll probably be the same. No, it will be a different number. Yeah, max and average are different. Um, we're not using reference samples yet. When we do, this gets much more interesting. Let's go to the right. After a little processing, sure enough, there's a bunch of noise on the left-hand side with the ant B signal. The B is referring to kind of a baseline math that I'm doing. I'm subtracting out the non-hydrogen, I'm dividing the hydrogen frequencies values by the non-hydrogen sample values. Um, I explain that more in the documentation. But sure enough, we see a bump now. This is getting better, although it has a bunch of noise on the front. We see two bumps at about 4,000 and way over on the right. It's interesting, the one on the right is kind of larger. This is the average after I do all that complication. Let's go to the next one. This is the same thing, but this is the maximum value of that calculated signal, is what I call it. We're going to do it again in a different way. Next. It's a little bit better, but not by much. This one is Ant RB, I can see on the left-hand side. We're way up in the top left-hand corner in the black, we can see that this is ezCon 116. So you can see we've just been counting along here. Not all the numbers are used, but at least we're doing it in somewhat of an order. Ant RB is another calculation, but it tries to use reference samples. You earlier talked about in astrophotography how you take pictures of the stars, But just so that you understand how your instrument works, how good the camera is, there might be imperfections. You also take a picture of essentially a white sheet or a white screen, and then you also cover up the telescope entirely and take a dark, which is with no light coming in instead of all even light. So whites and darks, there's lights and darks.
And biases. Yeah.
Um, this is what reference samples are like. I'm comparing the hydrogen sample signal from the antenna to other references and noting the differences. In my case, I've been doing division instead of subtraction. All right, so AntRB has something to do with references, and for each sample, there's an average. That's what we're plotting. The next one is the maximum for each one of those samples. You're seeing a whole lot of these things looking about the same, and that makes sense. Let's go to the right. And then I said I threw away some of those troublesome frequencies above and below. And wow, this is about related to those pretty yellow dots we saw. And sure enough, this graph looks better too. Uh, we had a screen with kind of a wiggly yellow line going across the middle. And this is the average value of each one of those vertical lines. For each one of those samples, what is the average value? The next plot, you could guess, is the same thing, but what is the maximum value of each one of those vertical lines
Wow.
that made up that yellow dot image we saw before? I have found that for very weak signals, maybe max is good. It's interesting. It certainly identifies large spikes that I didn't intend, that didn't come from hydrogen, that might have come from my neighbor's garage light or something. I don't know. Um, it could have come from lightning nearby, but they show up on these graphs, particularly in the maximum graphs, and that kind of makes some sense. Let's go to the right. This is all those plots together, plotted together from top down to the bottom. This is how kind of a history of the math that was created to make this go. And we spoke earlier how the current software you're using has ezCon astromath with a value of 1, the default. And that's why those little bumps don't line up with the little black lines going vertically. I think what we should do is go back and run it with that's because there's a bug in my ezCon Astro Math 1 math, some software bug that I got to figure out. Luckily, we have ezCon Astro Math with a value of 2 that uses the AstroPy Python library, which is much more authoritative than any code I came up with. So we're going to go do this same thing and come back to this plot and see if they line up better using AstroPy's math. The only problem is AstroPy's math just takes longer. So rats, I'll have to fix my code. Okay, so you ran all that same data, but this time with ezCon Astro Math with the value of 2 to avoid the bug in ezCon Astro Math with a value of 1, some bug I need to go fix. So we used the AstroPy library, which just takes longer. This took 20 minutes, and I think the first one with the value 1 took 3.5 minutes or so.
Right.
But this data turns out to be better. When I look at the purple little bumps and maybe the green bumps uh, at near the 4,000 sample, they line up with the black vertical line. This is what I'm looking for.
Now, this block vertical line, what does it signify?
There are 2 of them at the left and the right,
Right.
And those are defined as a little line going up when the galactic latitude crosses 0 degrees.
Okay.
Now let's figure out what that means. Galactic latitude, if you're looking at the plane of the galaxy, that's up and away from the plane. That's what latitude is. And it goes up to the North Pole at 90 degrees galactic latitude, and it goes down to the South Pole at minus 90 degrees latitude. But when it crosses through the very busy flat pizza of the galaxy, that would be at galactic latitude 0. And that's probably where all the action happens. And so I draw a line there. That's where all the stars and the gas and stuff are. And sure enough, that's why the bump appears in your data. Uh, the, the bump in your data aligns when your antenna was pointing at the plane of the galaxy at
Okay.
galactic latitude 0. And so I draw a line just for reference. If the bumps align with that vertical line, that's a good sign to me. Now I can tell you which one is which. Um, towards twice a day, I say most drift scans will cross the plane of the galaxy. Uh, one of those will be pointing closer towards the galactic center, where all the stars and gas are collecting. And about 12 hours later, it'll be pointing directly away from the galactic center, probably where there isn't much out there beyond Earth, beyond the sun and Earth and everybody. Um, towards the galactic center will probably have more hydrogen and therefore a stronger signal. After study of this, I've determined that as time increases to the right, if that blue galactic latitude in degrees curve is going down through the 0 mark, that is closer to the galactic center. And so I say the bump on the right is going down, and that will be the higher bump in purple and green. We see it here.
Okay.
There's even a bump, I suppose, in the orange. Yep. And that the black line on the left that you're pointing to now is pointing away from the galactic center, or at least farther away than the other black line. Okay. We see that in some of the other graphs. If we go to the left, for example, I think we'll see the purple one kind of highlighted. Left arrow, or find your clicker on the left.
Oh.
There it is. The bump on the right near the end of our sample, near the end of the data file, is a little bit bigger than the one on the middle. I say that's because it's towards the center of the more towards the center of the galaxy. Not directly at, but more towards. And so there's more gas there. It'll be a bigger bump.
Fantastic.
Anyway, so that's some of the math. This should hurt your head. That's how learning is occurring. That's good.
It's hurting, but it's hurting good.
That's good. The hurting goes away with repetition. Eventually, it starts to sink in. Let's go to the right. Here was the graph we were looking at that had the whole progression of all this stuff. As we go down the graph, it kind of gets better. That's not always the case, but in this case, it kind of was. What we need to do is run this data without all that noise on the front end. Right now, that would take a long time, so I'm going to ignore that for the moment. We should have thought of that before. Oh well. There's a way to only choose samples starting at maybe 2,000 and the rest of them. It's just more stuff you write on the command line. Let's go to the right. Okay, now we're going to go through all the stuff that we write into the output data file. This is, oh no, I'm sorry. We're going to look at the azimuth. You said you didn't change it. It was pointing south at 90 degrees up. I don't really know what that really means. It could be to the east, the west, as long as it's up in this case. But normally you point your antenna to the south and then point it up or down. If we go to the right again, that's the other one. It's at 90 degrees elevation, straight up, and it never changed. At least that's what you told all the samples.
Correct.
Go to the right. All right, now we're going to walk through how we got some of this math. These are all the raw samples with a dot for a value of the average of each spectrum. I don't know if I want to get through all this. It's helpful for debugging strange data. Let's go to the right. Turns out this is the same thing in a different color, because every one of those raw samples is an antenna sample. There's nothing to do with references. So it looks very much the same. If we go to the right, this is the seconds between samples. On the scale on the left, the Y scale, it's like either 8 seconds or 7 seconds, and it oscillates between those. So that makes the average at about 8 with all those speaks. Some of the spikes above were where the PC took longer than 8 seconds between samples. And I think that's because it was busy doing something else, or updating some Windows file, or writing to the hard disk and cleaning up the hard disk. There's operating system stuff that happens all the time. And there's no guarantee on precise timing in Windows. And this shows some of that. If you turned it off and came back, there would be a great big spike where there was a big gap in time. But mostly the time is either 7 or 8 seconds between samples. I have, with your easy, no, I'm sorry, with your SDR Sharp receiving program and the IF averaging plugin, the timing between samples has often been, it's been like 3 minutes or so. It takes a whole lot of samples, a whole lot of readings before it ever writes it down to an entry in the data file. I call an entry in the data file a sample. A sample is made up of many, many readings. Since you use the default that I put in the ezCon program for collecting, it took 31,000 readings for every one sample that was written to the data file. And that took about 7.5 seconds, as shown on this graph. Okay, this is for the raw samples. Let's go to the right. I keep telling you that in this case, all your raw samples are all ant samples, so it's the same graph in a different color. If we go to the right, you don't have any ref samples, and so I can't plot it. And this is what in case you had an earlier one, I step on the old file just to make sure you're aware and updated. Let's go to the right. Now I go through all kinds of math of how we calculated this. Some of these are copies of earlier plot numbers that you saw before. This is ant raw, the average. Let's go to the right. This is before any filtering. This is after any filtering. This is going to be dull. We're going to walk through these quickly. Next. Here's the maximum of each one of those samples. We can see a little bit of a bump, but gosh, there's a whole bunch of noise on the front that's polluting our data set. Next. References, I told you that I'm faking it and just using the first one, so no wonder it doesn't change. Next. You've seen all this before in an earlier discussion here. Next. That's the maximum. Here's a baseline. This is some of the math that I go into in some of my documentation, telling you how I come up with ant B as a signal. The B had to do with baseline. This is the baseline itself. This is the strength of the frequencies that should not have hydrogen in them. It would be good to, so this is like background noise. It would be good to remove this from our analysis. Next. Once you do, suddenly the hydrogen shows up. This is the hydrogen divided by that baseline, or the antenna divided by the baseline, and suddenly the hydrogen pops up a little bit better. We got two bumps. The one on the right is bigger. Next. This is the same thing, but these are the maximum values, not very helpful in our case. Next. This is ezRA. It's kind of an intermediate value. It has something to do with the background value um, of of the whole of all the samples. Next, we use that to create. And from that we get a baseline in the same way that we did before. Let's go to the right, and we calculate ezRB using those earlier partial calculations. It's all in the documentation to some degree.
Okay.
It's certainly in the code. Go figure it out if you wish. I spell it out, and I will spell it out better in the time. Maybe this gets better because it's using references, but again, this data set doesn't have any references in it, so I don't expect this to be much better than the green stuff we saw before. You can see that as we keep progressing, I use the same color scheme for each set of data as we go along. This is the ezRB in, it's called orange, looks kind of yellow to me. Next. Here's the maximum values. Sure enough, we can see little bumps, but they're not very big. It mostly has all that noise on the front. Next. We've changed colors because now we've either chosen the green signal or the orange signal and are progressing farther along with it. We have trimmed off some of the frequencies, high and low. Apparently not enough from what I see, because we still have all this noise on the left. Let's go to the right. This is after we put on all that velocity correction stuff. The velocity correction stuff is called velocity from the local standard of reference, VLSR, VLSR. And so that's why over on the left, the signal name has a V on the end, because it was corrected with the velocity information. Let's go to the right. And then finally, we trim off some other frequencies, and the graph looks better and better. We got rid of some, at least the spikes on the top. The spikes on the bottom don't bother me too much. They just kind of become blank spots on the graph, and it's not that important. And so this was the graph that looked best. We saw that as a yellow spot in the middle and a yellow spot over on the right long ago. Let's go to the right. So these are the things that get written out to the data file. The data file ends with period EZB. EZ, of course, just like ezRA. And I didn't want to use A, so I used the letter B. I defined EZB to be a certain format as a as an output from ezCon. Next. All right, those all graphs had sample number along the bottom. Now we're going to look at the average sample across all the samples and what is the shape of that spectrum. On the bottom now we have frequency around some center frequency. We know that center frequency is 1420.405. It was even on earlier graphs. We are taking measurements at each one of those frequencies as we go from left to right. All of those together make over many, many readings makes one sample. In this case, we've taken all the 4,000 or 8,000 samples. I think 8,000.
It's about 8,000, yeah.
And averaged them together. And so we see the general shape of,
Oh, wait a minute. Was it 11,000?
well, let's go back one plot.
I think it was 11,000.
Let's go back one plot. It's shown on the very bottom line as 11,400.
11,470.
So anyway, all those samples averaged together, but this time not as strength, but as frequency values. So this may hurt your head again. That's okay. Let's go to the right. And that's the spectrum that you get. It turns out for the center spectrum near zero, it's nice big number. But electrically, there's some filter stuff going on, and you get this funny three bump stuff. And so on the very edges on the left and the right, it's a very low number. The analysis of this ezCon program tries to remove that in many ways. Some of it is simply trims it off and throws it away, and otherwise it tries to flatten the curve using that information. We do see some oddity in the middle. Well, first off, there's a little spike over on the right in that little valley, and there's another spike on the left over there. So at some time during that, it changed the average spectrum value because of either something really loud once or twice, or a consistent noise that was kind of small. I don't care, it changed the average. And in the middle, it's not quite round, so something's going on with hydrogen. That was from those yellow splotches. Let's go to the right. That was the raw data. I tell you that the ant raw is the same as the raw data because you don't have any reference samples, and so it should look just the same in a different color. Let's go to the right. After your filtering, but we didn't do any filtering, so no wonder it looks the same. Let's go to the right. And then here's the spectrum after we cleaned it up a little bit. Well, actually, no, these are the maximum values. So, oh my gosh, at some point along that data file, there were some values that had big numbers compared to the other ones. So there was some loud noise at a low frequency and also up at a high frequency.
This is a whisper. This is the whisper transmitter, I believe.
Oh yeah, okay. Um, and the data noticed it too. Let's go to the right. The reference is really a picture of the very first sample. And so this is what it looked like. Apparently there was a little noise on the left-hand side in the beginning of our data file. And yeah, we kind of saw something like that. It's a little bumpier because it's not averaging over a whole bunch of samples. I told you that I'm cheating, and since you didn't give me a reference sample, I'm using the very first sample to compare to. All right, that's fine. Let's go to the right. And here are the maximum values on that reference spectrum. Since it was one set of values, I guess the maximum of one set of values is that same set of values.
Sorry. There you go.
Yeah, and so that kind of makes sense. Let's go to the right. Here's ant B, and so where I'm doing a little bit of processing, it looks pretty much the same. Let's go to the right. Apparently it had large maximums in it as well, so we need to do something to get rid of those. Let's go to the right. Here's the ant RA average spectrum. I hardly have any idea what this really means. It's an intermediate value that is kind of looking at the background. But I thought for completeness, sure, while I'm at it, let's do a spectrum of it too. Maybe I'll understand it better later on. This was the average over all those samples, all the 11,000 something samples. To the right. And we finally come up with ant RB. It has the same kind of diseases as far as spectrum goes. Something's kind of dropped in the middle. Okay, let's go to the right. It also shows some loud spikes, bigger than other samples. And since it didn't show up in the average, they must have been a very short time period where these maximums showed up. Okay, that's fine. Next. Now what I do is on the left and the right, you can see it's a straight line at value 1. The ezCon program simply trims off those values and sets them to 1. It steps on them. It says there should be no hydrogen way out there. Let's just remove it. It might change the spectrum a little bit, or it certainly will change the edges of the spectrum, and it might help figure out other things as we go along here. Suddenly, there's a whole lot of information going on in the middle, as if there was a consistent source of noise in the middle, and that's the hydrogen peaking up in the middle. It's kind of blurred because it hasn't been corrected for velocity yet. Let's go to the right. Now it's a little bit corrected for velocity and it kind of moved around a bit. That's interesting. Go to the right. The name of the on the left hand side is the ant signal chosen from someplace. That's what the X means. It got trimmed, then it got corrected for velocity, and then I trimmed off the edges again. And that's those yellow blobs down the middle of that colorful graph we saw, showing up near the 0 frequency. On that graph, they were in time across the middle of the plot. In this case, they're all bunched up in the 0 in the middle of the plot going up to the right. And then I rotate the graph just so that you can find the frequency bin. For example, we know there's a frequency loud noise that we might want to trim out and simply throw away that frequency channel, that certain value of frequency at about 170 or so, that big spike on the top. It might be good just to make it go away. Just throw away all the information we have for that frequency range. There's something printed out in the plot, in the program printout. Remember all that text flying by?
Yeah.
It will tell you exactly what that number is. Problem if it'll tell you what the big one is anyway. It'll tell you the biggest change along that wiggly curve and what number it is. But I just drew it on its side so that you could get a better number for the frequency bin on the left. Next. Okay, so now we're looking at the maximum spectrum after all that, and we're starting to see kind of a shape to it. This is the maximum spectrum that showed up in the middle instead of being mushed together as an average. So there was probably a sharp yellow bump that had a peak on the left, and there was probably a bright yellow bump in the signal, that blob, and it probably has a peak on the right. Okay. I don't know if this is helpful. Sometimes it's helpful for debugging. In this case, it's just a bunch of information that's kind of overloading. Let's go to the right. All right. For those samples that were defined as close to the galaxy plane, so when we were pointing the antenna towards the plane of the galaxy, what were those spectrums like? And let's average them together and make a plot. So the galactic longitude is now on the x-axis. Wow, that's something new. The center of the galaxy would be the center of this black plot, right in the middle, at 0, 0. The velocity has now been corrected for. It's not just frequency, it's velocity. And we are plotting velocity of that gas and how much it is going away from us. That's a positive number, going away from us, versus where it is as we look towards the center of the galactic pie, the galactic plane, where galactic latitude is 0. Okay, for all those things, you start getting very interesting stuff, and you can start seeing parts of the galaxy if you get enough data. This is not enough data. I mean lots of data. Along the top, the last data file that was used was MLO 221129 with a _00. That's the last file that was included. I had to write down something. You might update it, and you might have a new plot as the last a new data file, and so I figured that's what should be written up there. In the middle is the name of something. You can either define it as MLO, or it will take the first letters before all the numbers on that file that came from the left. It started with MLO also. And on the right is, in parentheses, is the program that created this plot. In case we come up with a better program, you might want to know what program plotted this. You're welcome to use an editor and take it out and turn it to white and make a better result to put in your report. So we have the next plot. Let's see what that one is. This is related to the previous plot. This is how many samples you have for each one of those galactic longitudes. It would be good if you filled them all in and had data for every galactic longitude. When you're looking at the pizza pie of the galaxy and you're looking at the center where 0 is, to the left is plus and up to 90 degrees off to your left-hand side. Behind you is 180 degrees. And so far, we only have kind of 2 sections. We want to fill in all those things. And the way you do that is you take drift scans at different elevations of the sky, and it will automatically kind of fill in. But you got to do a whole bunch of it. All right, let's go to the right. So this is count. This is not value. Next. This is like the plot 2 previous before, except wrapped around in a circle. The left side of that black plot before is pointing straight down. The middle of that plot is pointing straight up, and the right side of that earlier plot is pointing straight down again. It's simply wrapped around.
Okay.
They show up as the same place as the numbers. This is like the sun in the center, and you are looking at the velocity information as you swivel your head around. Sometimes you're looking straight up at the galaxy center, and sometimes you're looking off to the left or the right or behind you. It's interesting.
Very.
Next. This is the same plot, except now with count. How much data do you have? It would be great to have a really bright number everywhere. But this is kind of a graphical view of where you need some data. Apparently, these two were not anywhere close towards the center of the galaxy, which would be straight up. This is count, not value.
Okay.
Next. Then you can plot it differently. If you change the x-axis on the bottom, that's galactic longitude, just like before. But now the y-axis up the left is declination, so minus 90 to plus 90, from the South Pole through the equator all the way up to the North Pole of the celestial sky. Where did you collect data? We saw earlier that the declination that you collected data was, because you were pointing straight up, was equal to the latitude of your antenna's location on Earth. What was that number? 30 what?
34.13.
Okay, well, it's convenient that those two things line up at about 34.
Right.
And that's where you were looking at the galaxy. It's an interesting plot. I'm not sure it has a whole lot of meaning, but I was not able to predict what it would look like when you get a lot of data. I thought it was interesting. Next. On earlier plots, we want to know what is the highest frequency that the spectrum reveals. We know the spectrum moves left and right. That has to do with the gas moving, let's see, towards us and away from us. And I want to know what is the highest possible frequency of that spectrum coming from the hydrogen, not from noise. And this is plotting that. You have to tune another knob, and that's why there are a whole bunch of numbers over on the left-hand side to get the right result. And so I just plot this with all kinds of different values, and I pick out the one that I like the best. The uppermost frequency is in red, and the lowermost, well, actually, this is in velocity in this case, a little conversion. The lowest velocity is in blue for
So
these
this is like
particular
radial
models.
velocity. This is telling me that.
No, that's a different thing. This is well, yeah. Um, this is velocity from the antenna after correction, having to do with the Earth going around the sun and such.
Okay.
This is important later on for the next graph, where I try to plot the rotation speed around from the galactic center out. We don't have enough data for this plot to make any sense at all. You need a whole bunch of data, and you get a curve, and it's interesting. It's not what Newton would have predicted, and we think that's pretty intriguing. And you could plot it to getting enough data. Next. Okay. Yeah, all right. Well, this is another way to plot data. This is new to me. I'm trying to remember what it was. Um,
Corrected by velocity
well,
TV.
yeah, it has a V in it, so I know it's corrected by velocity, and that's interesting. But I think I actually would normal. Well, I was discussing this with somebody, and we had to come up with this plot. Um, I'll make more sense out of it as we go along.
Okay.
Let's go to the right. Okay, now for every time that you got data near the galactic plane, I kept the average spectrum. So as you click to the right, you should see this bump move around to the left and the right. Right now it's a little bit off center to the right of 0. And the values over on the left change a little bit, and this bump should move along. It's better when you get more and more data, of course.
So it's
Going to the right, there'll be a bunch of them. I do this for every single degree of galactic longitude that you have. And you can see it moving along. This is kind of like the movie thing you were doing. Let's do a mouse scroll wheel down and bring it back. There you are. You got zoomed in somehow.
yeah. I don't know. I don't know.
And that's how you get back. So let's do left and right, and we can see that this changes. So as you look in different places on the galaxy, you get different spectrums, and that is helpful. This is somewhat like the movie that you were looking at before. I
Yes.
think what happened was you ran out of plots. You clicked on the right where there was suddenly no arrow, and
Exactly.
something else went wrong.
So this is the last one.
Apparently so. There's
Yeah.
no arrow on the right, whereas there is that arrow on the left. Okay. Now
Fascinating.
with one declination, you got some data. You want more? You want more data overlapped on top of this? You called it stacking before, to get a cleaner curve and all kinds of stuff. But ezCon will calculate it and try to provide what it can from the data you provide. That's kind of a quick overview of the simplest use of ezCon. There are lots of knobs and switches to change on ezCon to improve the results, and there's ways to get better and better data feeding into ezCon. But you and I are going to now try a new version of ezCon and see if it makes a difference on your machine.
Sounds good. I'm going to stop this recording right now. I want to thank you so much. This is for the recording, for the great explanations, and then we're going to go into other chapters where you're going to explain the different programs, and we're going to start with the new ezCon call, which is it's going to be newer with less bugs. So
No, I'm
Thanks
not sure about that. It's experimental. We're going to find out together,
for
and
experimenting.
we'll see how if I can explain them all.
Sounds
But
good.
otherwise, we want you to help explain them all you volunteers. Thank you.